Welcome everyone, and we are starting our ninth colloquium, which is very exciting. A few words about Carinas before we start. This started, officially it started in 2022, and what we had in mind at the beginning that uh, between PhD and postdoc, we start losing women, and we wanted to do something which is more long term, and we start having more and more women coming up at the top level. And our approach was that we wanted a bottom up approach so that we can do activities and things that encourage more women to come participate and be present and not lose out that whole candidate pool. As far as Carinas is concerned, we are basically doing several things, and we started off with small steps. So one of the initiative was our newsletters, where we not only highlight the science done by Indian women, but also generally their lives and what the struggles are in their careers. And basically, we went from previous generations to current generation. In the most recent one, which will be out soon, we have younger women in that newsletter. The other initiative is this Science Talk series, where we are very happy to say that almost everyone we approach came and gave a talk. So we will be soon having 10th colloquium, and it's basically coming to a 1 full year of talk series. There is one more initiative which is very recent, and many other members are very actively involved in that effort, which is called Galpal team. And here, the younger women are being mentored successively by the more senior women, and there is a two-way channel, like someone at the mid-career level can be mentored by a more senior faculty. And it has been going great so far. It's been quite a few months. So overall, we have 3-4 different new things, and we are very much happy if anyone wants to start something new within the umbrella of Carinas. With this, I think I will be happy to give to Monami for our speaker introduction. And before we start that, I think I'll introduce Arpita, who is actually my mentee in the Galpal program, and she's going to take over some of the hosting of this colloquium series. Today she'll be doing the Q&A. She will completely take over from us at the end. So with that, I'll give Manami to introduce our speaker. Welcome, Suchetana.
Thank you, Prakriti. And thank you, Arpita, for helping us out. And also for the first time she's doing. So huge clap for you. And welcome, Suchetana Di, in our today's colloquium. Professor Suchetana Chatterjee currently is in Presidency University. She did her bachelor study from the Presidency College, and then she went to IIT Kanpur in 2001, and then completed her master's in physics in 2003. She completed her PhD in physics with specialization in cosmology and astrophysics from University of Pittsburgh. And then after that, she went to Yale and then UMing as a postdoc. And after that, she joined Presidency University. And since then, she was there, and she has been a great mentor to a lot of young people. And so, welcome, Suchetana Di, and take it over.
Okay. Thank you so much, Monami and Prakriti and others and Team Carinas. First of all, my congratulations to the people who actually started Carinas. And I think I was privy to that moment when Karina started. It was just a based on a Facebook post, and felt immense pride to see that many of the youngsters coming forward and taking such an initiative. And particularly also thank you so much for inviting me to your monthly colloquium series. I also want to apologize because I also registered as part of the GALPAL program, where you want to mentor a younger scientists from the community. But you all will know that once you become a faculty member, it's just your time becomes so strained that I couldn't do much. And so I apologize. I hope to catch up with the mentorship program as much as possible. Now, so that's my public apology to the people who actually got in touch with me, but I could not. I thought that I'll talk to them, but couldn't. So I apologize. Okay. So I think many of you are probably the people who are here today are aware that we people in Calcutta and even in all of India, we are having a very, all of Bengal and all of India, we are having a very both dark and bright time in terms of an event that occurred like a month back, which involved workplace violence involving a young doctor who was 31 years old and was working, a woman doctor. And there has been like immense social uproar on the event. And there had been a lot of talks about how to make workplaces safer in general in India, and particularly safer for women in India. And I am like very much, part of this thing that I wish that I could give the talk at happier times. But the happy thing is that, yeah, people are now thinking or talking in terms of positive, constructive things. But it has been such a distracting and disturbing time that I wish that I could have spent did more justice to the talk, because it's really an honor for me. So without further delay, let me try whatever I could have put forward, and I wish that we will have some intellectually stimulating discussion with the talk. Okay. So the title I gave is A Cosmological Evolution of Supermassive Black Holes, a multi-wavelength approach. Now, this is indeed a pretty broad title, and there are so many aspects to it, facets and aspects to it. So it's very hard to say that what should we concentrate. So let me try to build up some part of this story through the work that I have been involved in doing over many years. And I would start the talk with this beautiful simulation. So the idea is that I will show you this simulation, which I'm sure some of you at least definitely have seen. It's a little bit older simulation from the elastic stream. And what my talk will be is to try to construct the beautiful imagery that we see in this simulation. I'm sorry, this is a YouTube video. Can you see the video?
No, till now.
No.
So can you see it now?
No, we can't hear the some sound, but the video is not.
The video? Okay. So let me just stop the sharing and then reshare the video, and let's see. So let me go to Zoom. Okay. And let me share the screen. Okay. Can you see the YouTube thing now? Can you see the screen now?
Yes.
Yes. Okay. So what this video is about, it will be clear in a minute. And what I'll try to do in this talk is to reconstruct some of the visuals that you see in this video. and I'll tell you how we go with the story. Okay.
Suchetana, we cannot hear you. Are you still speaking?
Yes,
No, in the sense that this is louder. The audio of the
audio is louder. I can
yeah.
just move the volume. So what you are seeing here is formation of structures in the universe, and you have dark matter, gas, and also you have active galactic nuclei, and you see these large blasts of energy coming out.
I think if you put the video on, your voice goes down automatically. It's using. We cannot hear you. If you pause the video, we can.
I understand why. Okay. Can you hear me now? Okay, great.
Yes.
So what we saw in that video is actually a simulation from the Illustris team, and that is effectively the evolution of the universe over the last 14 billion years. And so what I'm going to do in this talk is actually trying to, say bits of things to connect what we saw in this movie. So some aspects of the thing that I would like to discuss. So let's now get to my slides again. Can you see my slides now? Great. So let me go from the current slide. And now, as all of you know, that the simulation that I showed had an underlying cosmology, which is our very own lambda CDM cosmology. And then there can be questions that, okay, what is the degree to which we believe lambda CDM? I'll not get into that. I'll just get into the picture that we saw. And of course, there are lots of missing points in this story. But the underlying physics of this simulation is the lambda CDM cosmology, which came over decades of observational and theoretical effort. And then you have the dark matter in the simulation, which are kind of particle which goes beyond the standard model. So you do not have understanding of what the fundamental particle model of dark matter is. There are candidate particles. But what you do for this cosmological simulation is that you know that they interact with each other via gravity. And for our purpose, the unit of structure formation. This is like a cosmic wave. This is just a snapshot from a 20-year-old picture, the Millennium simulation. That is much older. That was in our times. And what you see in this snapshot is actually the cosmic wave network, but this is just in dark matter, and this is the dark matter. This is a dark matter halo, a massive collapsed gravitationally bound object. Now, in the paradigm of the cosmological simulations that I'm talking, and our understanding of the universe, it's not just dark matter. We saw in the lambda CDM paradigm that the majority of the matter in our universe is indeed dark. But then what we see as astronomers is light, that we look at galaxies. When we look at large-scale structure in the universe, we actually look at galaxies. And so this is again one snapshot again from the same Millennium simulation. And what this picture tells is that apart from dark matter, which is easy to do in simulations because they just interact gravitationally, what you can do is you also put gas particles or stars in your simulation. That's one way to do and put light or put baryonic matter in the simulation. The other techniques that a lot of people use is the semi-analytic technique, where you take the dark matter halos and then you model in a semi-analytic way. You have analytic models for galaxy evolution. You paste them in your dark matter and find out properties of galaxies. So this is also a plot where you try the hydrosimulation. This is called hydrosimulations, where we have gas and gas particularly. There could be stars also. So what this picture shows is that you take these hydrosimulations and you make mock catalogs of galaxy, which is done in Illustris or all other simulations that some of you know of. And then you try to match and see that how are the predicted galaxy distribution agree with the observed galaxy distribution. So the ones in red are the predicted ones from simulations, and the ones in blue and purple are the surveys that you actually do the observations with. And what you broadly understand is that the hydrosimulations or semi-analytic models were great even like 15 years back in decently predicting the large-scale distribution of galaxies in the universe. Now, the point is that, so in the CDM paradigm, we know that the majority of the amount of matter in the universe is dark, and they interact gravitationally, and we form these dark matter halos. So you can have a mass function of halos, and then in your modeling, be it hydrosimulation or be it semi-analytic techniques, you just know how to paint your galaxies in this dark matter halo. And then you go from mass to light, and this is a luminosity function of galaxies. It's just a cartoon picture taken from one of Joe Silk's slides. And what you crudely observe is that the predicted ones, that means your CDM predicted dark matter halos, and you paint your galaxies on your CDM predicted halos. There must be a connection between how you go from mass to light. This red is what you predict from theory, and blue is what you see from observation. So the key observation is, this was again 20 years back, 15 years back observations, that at the low luminosity range, there is a huge mismatch with the prediction. So there is lower number of galaxies. And even in the high luminosity range, you have lower number of observed galaxies than what you predict from your theory. And so there must be some other mechanism operating which are actually suppressing star formation in these low or high mass systems. Now, one of the predictions was that in the low mass system, you have supernovae feedback, that's stellar feedback. Supernova feedback. There could be stellar feedback, that's not significant. And in the high mass range, you have this active galactic nuclei feedback. So this observation, and then when the galaxy luminosity function, and then at the similar time or like little bit before, when maybe in the same time, when people saw this interesting correlations when they tried to look at AGN host galaxies, and measure and found that there is a correlation between the central mass of these. Well, they're not necessarily AGN. They're just galaxies that have supermassive black holes. The black holes could be active or not. But when you try to measure the velocity dispersion of these galaxies, there are multiple methods to do that, and over different, morphological types of galaxies, you find a correlation between the central black hole mass and the velocity dispersion. So the paradigm that somehow the black hole that is sitting at a very small region of the galaxy, okay, the galaxy could be like hundreds of kiloparsec, and this is a small region of the size of a solar system or a little bit more. If you think it's a parsec, maybe even sub-parsec. How is there a method through which this central engine, this central black hole, is talking with the large-scale gas and stars spread out in its host galaxy? And that came the paradigm of galaxy coevolution. It says that maybe the growth of supermassive black holes in the universe or the evolution of AGN in the universe has connections with how their host galaxies evolve. That's the first thing. And the second thing is that there might be a connection with the overall large-scale structure of the universe and a connection between the growth of supermassive black holes. So they might be part of the cosmic wave, where now you have to take your supermassive black holes seriously. So I see a comment in the chat. Is there a comment? Somebody wrote something, I don't know. Okay. So now one of the proposals that how are these central engines or central black holes talking to the host galaxy? And so this is a famous, very, very famous poster child taken again 15 years back through multiple X-ray and radio and optical observations. So here you see a galaxy cluster. This is not a galaxy. This is a galaxy cluster. And you see a central AGN sitting here. And you see this large radio jets emanating from the galaxy, from the central engine. And what you see in blue is the X-ray gas in that cluster. You see a lot of X-ray gas in clusters. The key thing, I don't know how much it is visible in the screen, is that where you see these radio lobes or this, radio emission from the jets, you do see, hollows. You do see less emission in the X-rays. So these are like X-ray cavities, pretty big in size. And then came the paradigm that, hey, so the supermassive black hole, through a phenomenon of, injecting out energy and particles into its environment, might have impact in the star formation history of its own galaxy. Okay. So that's the paradigm of AGN feedback. But then the question is that you see the systems clearly in clusters, whereas when you do your M sigma, or when you talk about our galaxy luminosity function, these phenomena, if it is at all explaining the mode of communication between the central engine and the surrounding of the black hole, then it must be a universal phenomenon. So what happened is, now for the people who are running cosmological simulations, as I said, that the simulation community, as we saw in the movie, is trying to recreate the universe through theoretical modeling. I mean, that's a crude way to say. So you are actually trying to find a model of the universe. Now, this was the first set. I think it came 2005, was a small box, and then Demeter et al. In 2008, when I was a graduate student and I got the chance to work with the first set of cosmological simulations, where now people tried to input supermassive black holes. So you had dark matter, good. You had gas, very good. You have stars, some way you put stars in your simulation, and now you put black holes, supermassive black holes in the simulation. Now, how you put supermassive black holes, that has been a long debate. There's a long thing for that, because we can talk about that. But this is one of the first ones, which was a very small box, 35 megaparsec size box. And this was one of the first successful simulation that could include supermassive black holes. And the goal was to see that these black holes actually cosmologically grow, and they also feed out, they also give out energy into their surrounding medium. And using this so how do you model this growth and feedback of supermassive black holes? That we can discuss later. There are many ways to do it. There are some ways to do it, and there are debates about that, but that will come across the talk. But the whole idea was that so the way these people first tried to do is that they use the local M sigma relation. So you want to match your simulation output with your local M sigma relations, which is an observation, which is an observed thing. And then you input your black hole parameters and things into the model. But then the key thing is that, so since we do not know how supermassive black holes actually came into being in this universe, so there must be some hand-waving way of putting them in. And it was a purely phenomenological thing, that you see a phenomenon, which is the M sigma relation, and using that you tune your model. And then comes the next step, that once you have supermassive black holes in your simulation, you can now recreate, or at least make some prediction about this entire paradigm of galaxy coevolution, galaxy black hole coevolution, and design a bunch of experiments and test that how good is your modeling of supermassive black holes in these simulations that can be at least taken seriously to a certain degree, okay? Now, when it comes to, because the title is Cosmological Evolution of Supermassive Black Holes, so then so these are some of the questions. There are a long list of questions, but some of the questions that how do supermassive black holes form in the universe? There is a cute question that what is this mass hierarchy of black holes? There are stellar mass, supermassive, and now we know of intermediate mass black holes. Well, how old are SMBHs? That's the reason I write this, is because that this is the question that when do you first see the supermassive black holes in the universe? How does accretion actually, what are the modes of accretion that happen in supermassive black holes? What is the mass function of supermassive black holes? How does outflow come from black holes, etc.? And also the microphysics for coupling of gas and SMBH outflow. So how the energy or particles that get out of the black holes couple with their surrounding medium. All of these are very, very important questions. Of course, how does it impact the evolution of the galaxy? So these are all astrophysical, cosmological questions that one would like to address using cosmological simulations. But let me tell you that having supermassive black holes in cosmological simulations have their own challenges. It is successful to some degree, but then there are issues. Now, this is actually a list of other more recent simulations that tried different techniques and different modes to sort of, yes, Prakriti?
So about your first question, it is a bit dependent on what seed mass you put, right?
Yes.
It is a bit difficult to address this question from...
That's right. So how do you put a seed supermassive black hole would matter if that depends on your accretion. So what people do is, if you have initially a lot of cold gas, and if it's accrete in an Eddington way, it will be not much sensitive to the seed mass that you are using. So that's sort of the way to get away with it. But then why such seed masses? That's not an astrophysical reason. We can come to that. But having SMBHs in, as you said, as we said, and one point you raised, that having SMBHs in cosmological simulations have their own challenges. So if you talk to simulators who do these kinds of work, which is not me, they're spending all their time on devising techniques that how can you more realistically, model SMBH in the cosmological perspective, okay? So now, in my story, okay, in my story, which is a bit of what you saw in the movie, I would like to sort of put two questions. What happens to the energy released? That is the feedback energy that we're talking about. And how are AGN connected to host galaxy evolution? So does the accretion phenomena, the accretion activity of the AGN, we saw that, yes, it does, but cosmologically, yes, it does. We see the MBH sigma relation. Now, can we even look at the aspect that how universally it is evolving, it is affecting galaxy evolution? So maybe these are two questions that some aspects of it we can discuss in this talk today, in this colloquium today. Now, I call it twofold way. So twofold way because you have the simulation community and the simulation community, and then you have the observations community. So now I have talked to people from both communities and also people who are in the interface community like me, who try to, not be in any of this group. I don't know that's bad or good, but simulators, they, as I said, that we do not have a basic understanding or a basic model, or like what should be the initial supermassive black holes mass function. We don't even know that at high redshift, what is the mass function of supermassive black hole? How do supermassive black hole seeds form in the universe? And more importantly, when we are talking about supermassive black holes in simulations, we are talking about scales that are much smaller than the scales that can be resolved in cosmological volume simulation. So that's another numerical challenge. So people in the simulation community, they lot of put stress on how can they improve their algorithms, what kind of ways should be better in modeling the black hole itself, the black hole sink particle, what can they do, etc. And what they try to do is they try to take feedback from observations, from reliable observations. Now observers, on the other hand, they have, I think they have more respect for the cosmological simulations than actually the cosmological simulations deserve. Let me tell you, I think observers believe the simulations much more than they should do. So what the observers try to do is they try to seek input from the simulators to interpret their theory, right? They think that, oh, this is a model that I can use to interpret my observation. Now, what I have been trying to do is a twofold way. What is that? So I try to design, so let's say the simulation, as I said, the simulation, for example, takes input from the M sigma relation. So the M sigma is a one kind of observation which is being used to have input to the cosmological modeling of supermassive black holes. Now what, but simulation is a huge thing. You can do a lot of things with them. So what I have been trying to do is that I use these cosmological simulations and I design complementary observables. So these are observables that had no role in the input of the simulations. The simulation has been run through the input of a different set of observations. And now you construct another set of observations or more newer observations, which would have the predictive power. Because let's say this simulation has taken input from observable A, and now I use this simulation to predict observable B and see that how good is this simulation in predicting or even explaining observable B. So that helps both ways, that you design new experiments and guide the observers. And the other way is that you can actually also tune your simulations and make your simulations better, because the more and more you compare the simulations with different sets of observations, that gives fidelity to your simulations, because they are very phenomenological, and also there are other issues in nature when it comes to SMBH in cosmological simulations. Okay. So now the first one that I would want to talk is the Sinaev-Zeldovich effect, and that is a very odd man out in the SMBH community, but this is now getting a lot of attention. So the Sunyaev-Zeldovich effect is a purely, it's known as a purely cosmological phenomena. So what the SC effect is, it's a secondary effect in the cosmic microwave background. So after recombination, after last scattering, when the CMB photons have been traveling through the universe, when it encounters hot electrons that are originated in the later part of the universe due to astrophysical sources, these hot electrons can possibly inverse Compton scatter the CMB photons. So one such reservoir of hot electrons, actually X-ray energy electrons, are galaxy clusters. So these galaxy clusters are large reservoirs of these high energy electrons, which are capable for inverse Compton scattering the CMB photons, okay? Now, the idea of this, now due to this inverse Compton scattering, what happens is that you actually preserve the number density of photons. So there is upscattering of your photon distribution. And now if you see this plot here, so this is effectively your observer, this is the loss scattering surface, and if there is a galaxy cluster, source of hot electrons, these CMB photons are now upscattered. So all of them gain energy. Now but the number density is fixed. So what happens is the spectrum of the CMB moves from the Rayleigh-Jeans to the Wien side. So it moves to the little bit high energy. The change in energy is very small. This is a very weak scattering, by the way. But what happens is very interesting, that if you now see this picture, this solid line that you see, this is hand-drawn by in the original Sunyaev-Zeldovich paper. The black solid line that you see is the original black body of the CMB, and the dashed line is what happens once you have the inverse Compton. So this is the SZ distorted spectrum of the black body. Now, this gain of energy, because you can see that everything is moving on the Wien side. This gain of energy is a process that is dependent on the initial energy of the photons, initial energy of the CMB photons. As a result of that, the shift is not uniform at all frequencies or all energies, and hence there is a departure from a black body. So there is a spectral distortion in the black body due to the Sunyaev-Zeldovich effect. And this, now if you take a difference, so this is the black body intensity at a given wavelength, and this is the Sunyaev-Zeldovich scattered intensity of the same CMB photons. So if you now take the difference, that is what is delta I here. So this is the change from the black body. And what you can see that this dashed line before this point in the left-hand side of this point are below the solid line, whereas the dashed line goes above the solid line. So that means these guys, these photons, are less in number compared to what they would have been in black body, and these are more in numbers compared to what they would have been had it been a pure black body. And hence, there is a deficit and an excess of photon, and that you can write, this is the intensity change. And if you go in a radio astronomer's language, this intensity change can be seen as a cold spot and a hot spot. So this is a decrement and an enhancement in the temperature. So the Sunyaev-Zeldovich effect comes as a temperature and isotropy in the CMB. Now, if you look at this point, this point where there's a crossover, this is a particular frequency at which you get the exact intensity as the black body. And this is called the null frequency. This comes around 220 gigahertz. Below the null, you see deficit. Above the null, you see enhancement. So that is the Sunyaev-Zeldovich effect. And the leading candidates are galaxy clusters. Now, this is this was my first PhD paper. So this was my first paper that I wrote in my life when I was a graduate student. what we proposed in that paper, and that idea was based on previous work done by other people. These are the pioneers who came up with this idea. The idea is that if the SZ effect is an effect so that whenever there is a reservoir of hot gas or hot electrons in the universe and the CMB gets to get scattered through it, you would see the Sunyaev-Zel'dovich distortion. So just like you can see large reservoirs of hot electrons in galaxy clusters, you would see that in the vicinity of an AGN due to its feedback effect, due to its accretion effect, so on and so forth. So there would be source of hot electrons in the vicinity of an active galactic nuclei, and that high energy electrons can possibly inverse Compton scatter the CMB photon. So this would be an additional effect to the galaxy cluster effect. So our prediction was that this effect is much weaker. We had some theoretical modeling of the things, and we found that we got a few microkelvin order temperature fluctuation in the cosmic microwave background that can possibly happen due to the feedback of the black hole. In this case, we talked about quasar feedback, or this is just AGN feedback. Of course, this number, that few microkelvin number, is dependent on model. So that was our prediction. But I think the more important aspect of our paper was that we were the first to say that how can you actually go and detect this, okay? And so what we did is at that time, ALMA was in commission. ALMA was under, it was not commissioned. ALMA was just on paper. It was not functioning, or test runs were going on. So we predicted that given the scale and the amplitude of the fluctuation, you could possibly detect this effect with the Atacama Large Millimeter Array. And then followed up with this work, we actually also did numerical simulations using cosmological volume simulations to see that what kind of experiment you need to have, or what kind of sensitivities you need to have. So this is from my paper, and what we found that yes, it is possible to sort of detect this effect, that the SZ effect from Sunyaev-Zel'dovich effect from black hole feedback using the Atacama Large Millimeter Array. So we also proposed two modes of detection. I'll bring the cosmological simulation aspect here. I'll tell you the black hole feedback aspect here. So the idea was that what if we use the SZ effect as a probe of black hole feedback, and maybe from numerical simulations, from cosmological volume simulations, we can predict the SZ signal and then ask our observer friends that if they can make a measurement and put a some constant. So this was designing a new observable. First, this is a fantastic effect, which is nice. Second, it gives us another route of observation to sort of, see what the simulations predict and test the fidelity of the models that go into cosmological simulations, okay? So this was 2007. I got my PhD in 2009. So that was many years back. And there were some work in between. So even in my thesis, we tried some statistical analysis to detect this effect in the WMAP data, but it was very tentative. Nothing was detected. There were other groups. And then in 2013, I came back to India. There were other groups who used actually Planck and ACT, SPT, to sort of detect the prediction that we made using, that is detection of black hole feedback using the Sunyaev-Zel'dovich effect. But those were all statistical work, okay? Then in 2016, I got an email from this gentleman, Dr. Mark Lessey, who's at NRO, and they were writing a proposal to detect this effect using the Atacama Large Millimeter Array, but now it is a direct detection. So by direct detection, I mean that you actually look at a quasar. Once this is not statistical, you actually look at a single quasar, you make gigahertz. So in the SZ bands, you actually make maps in some millimeter wave bands. You actually look at these quasars, look at their effect, and then try to see that indeed, if there is a detectable SZ effect, and if it is detectable, is it the same as the theorists are kind of predicting? They are trying to predict, okay? So this was the very first direct detection of quasar feedback where Leslie and his group, I was just picked up in here, but it's mainly completely an observational work where they actually use the Atacama Large Millimeter Array in the 130 gigahertz band and looked at a particular quasar, very nearby quasar, and had even multi-frequency, multi-wavelength observations of that to find out if you actually detect an SZ decrement. Remember, it's 130 gigahertz, which is below the null frequency, so you would expect a decrement in the Sunive-Zeldovich signal, in the CMB signal, and they detected that, yes, there is a detection of roughly 30 microkelvin that they can get. So the reason we said few microkelvins, that was again in the statistical aspect, the peak could be much higher than a few microkelvin. And as I said, it also depends on the model. So that was very much, this was the first time, I think one of the very, happy moments in my career, because ever since I wrote that SZ paper, I used to get very frustrated as a graduate student that I don't think it would ever be detected. Nobody would ever pay any attention to the effect that we talked about. But then when observers get excited about your work and they tell you that, we are writing a proposal based on the thing that you are predicting, and then eventually there was the detection, that was one of the very happy moments in my career. So inspired by these kinds of detection, and now there are actually a few systems, very few systems, but still these are very hard observations to do. We then, now since I'm now a graduate, now I'm a faculty member, now I stopped working and started busing students. So now we got this. So this was very much motivated by our first detection. We had a PhD student, Abhinanda Chakraborty, who is actually a Carina's member. I'm very proud to say that. And so Abhinanda, in her thesis, so we did this so Abhinanda did this work for her thesis, where what we did is, now we went much ahead, because remember, in 2007, in 2008, there were only 1 or 2 simulations that were doing black hole feedback at the cosmological level. But this is 2009, 20, 2021. So now we have a set of plethora of simulations with much more sophisticated algorithm where black hole feedback and black hole growth has been used. So one of them was this Dave et al. This is the SIMBA simulations. So we got hold of the Dave et al. Simulation. Now there are many aspects to it, but the key features that I would like to discuss with the Dave simulations and why we chose it is because in the first generation of cosmological simulations, there were models of feedback which were just like dumping thermal energy. Now then came the next generation of cosmological simulations where you could actually become brave enough, although again, it's still subgrid physics, so it's debatable that how reliable are these models. But what Dave and even some other groups, Dave was particularly, we don't know how much reliable their simulations are, but what was interesting about the simulation is that these simulations not only had AGN feedback, but had different models of feedback. So it could be mechanical in nature, it could be radiative in nature. And as I said, here there is a small table. This is a very bad nomenclature, though. So we had like 4 sets of simulation of the same cosmological volume. This is a 100 megaparsec box. These are some parameters of the simulation. So there are 4 sets of simulations, one that did not have any black hole feedback. Then there was a simulation where there was only radiative feedback. They called it no jet feedback. Forget about that, but this just had radiative feedback. And then this is, I wouldn't say radiative. By radiative, I mean actually this is also mechanical feedback. This is like wind, quasar winds coming. And then there was another set where you have both winds and jets. So you can have relativistic jets. As I said, it should be taken with a grain of salt because none of these simulations, even the best ones so far, do not have the resolution to really make a difference between jet and jet and winds at the level of the accretion disk or the BLR or things like that. Okay. So, but the modeling, the way the energy is being spread, that's kind of different. Okay. I see another question. Okay, somebody, there was a message, sorry. So now what Abhinanda did is, so there was a wind mode, then there was a wind plus jet, and then there was a wind plus jet plus radiative, which is called the radiative plus jet plus X-ray feedback. This is the all feedback mode. So there were 4 sets of the same simulation. And we did an extensive work in calculating, in predicting that if I take the same kinds of system, okay, because it's not exactly the same simulation, but it starts from the same initial conditions. So it's kind of a similar simulations. Please let me know how much time I have if I am exceeding the time.
Hi, Suchet. May I just, you have 5 minutes more, if that is okay.
Only 5 minutes? Okay. Okay. Okay, we'll see because Okay, I'll quickly, Okay, how long was the talk? Yeah.
I think it was around 15 minutes or something.
Oh, okay.
Around that, so.
Let me quickly go through it. So these are these 4 sets of feedback that was there in the simulation. And what Ovinanda found in her work, this is actually this is just a redshift. This is a redshift 1 map of 1 system, but 4 sets of simulation. And actually, you see that there are 2 sets. So this is 1 set of black hole. This is 1 set of black hole. We actually took 2 representative black holes, one that have the highest mass in the simulation and the one that had the highest luminosity. But there are 4 groups of sets for each 4 as the model based on what model of feedback is there. Now, it's a very tedious machinery because you calculate the theoretical maps and then you calculate also, Ovinanda did a lot of modeling on what would be the predicted signal for ALMA. This was all because we wanted, the guide our observers about the detection. So what the idea was that can we get different signals for what kind of models we are using as feedback? And this was the TDS table that Ovinanda and all of us had to prepare, which is that if we now look at different bands of ALMA, so this is in the ALMA nomenclature, it is 7431, and these are the frequencies of the bands, 320 gigahertz, 135, 142. And you can see that all these 3 bands, 135, 142, they are below the null frequency, the 220 gigahertz, whereas this one is above the null frequency. So here you would expect an enhancement, and these ones as decrement, and that's what is manifested in the plus and minus sign. And what we saw, so instead of the signal, if you look at the signal to noise, because this noise also had to be calculated, and for that we took a lot of help from Mark. Mark was the one who guided us. And what we found is that at high redshifts, that is roughly at redshift 1, as well as at low redshift, there is a good chance of detecting this signal if we sort. So whatever the theory, so the point was that there is a chance of detecting the signal as per predicted by the cosmological simulations, the modeling that Dave and colleagues did in their simulations. So if I have to believe the simulations, then I got to detect these signals at reasonably significant level. But the catch was the detection of these signals was only possible when there is no jet mode in the feedback model. That means once you add the jet in your simulation, as Dave has added the jet, once it's just wind or just wind plus radiative, we have enough signal that could be detected through this ALMA, campaign, ALMA observation campaign. But once the jet mode of feedback is being added in the cosmological simulation, it's not clear from here, but you can see this one, no jet. There is no jet. You can see these bright ones. Once you add the jet, all the signal is gone because the gas is being ripped off from the vicinity of the black hole. And since the Sunaev-Zeldovich effect, which I actually forgot to mention, is actually a line of sight integration of the pressure of the gas. So you have both density and temperature. And as a result of that, you actually lose all signal once you include the once you tune in the jet feedback. So that was the sort of the key message from this paper. Now, I'll just, because since I have very lack of time, I'll just quickly take like 5 more minutes. Now, you see, this is, I see the same, this is a clusters 3. So there must be some 1 and 2 before that. And I would not get into the details, but my previous PhD student, Rudrani Kaur Chaudhuri, what she did was she also used not just SIMBA, but 3 sets of cosmological simulation. And she used the APEC model, which is the plasma emission code model. And what she did is she actually modeled the X-ray signal from the same set of black holes. So Abhinanda used the same black holes to predict their SZ signals. And Rudrani, even before in her thesis, she developed the machinery to predict what would be the X-ray map. If this is the model of feedback, how would the X-ray maps look in this simulation for these different 4 modes of feedback? Okay, and she also found that once you include the jet, the signal just drops so much that you don't detect them. But the key interesting thing, this is Rudrani's theoretical map, and then she had to do a lot of analysis to get the observation map. So these are actually Chandra mock maps. So now if I look at the Chandra mock map, she actually predicted for Chandra. We can do it for other X-ray telescopes. And what we found, I would say, just the key message is that the findings were complementary in X-ray and SZ. In SZ, we saw enhancement of the signal. That means the SZ flux increases if you include feedback into the system. Forget about the jet. But for the X-ray, you actually see decrement. So if you wish to distinguish that what kinds of model are preferably trying to explain your observations, the best route would be to do a cross study of X-ray and SZ, and that might give you more constraints on what kind of models you can use in your cosmological simulations. Okay, so I'll not get into the details of that, but I just like to take 2 more minutes. This is a recent work. This is work in review. It's in ANA, it's in review. So one of the other things, I said multi-wavelength approach. So one of the other things that is very different, this is a new domain, and I don't even have much knowledge about that, is actually looking at, as I said, that we also want to know about the host galaxy properties. This is not related to the cosmological simulation problem. But what we tried to do in this work is we took a set of AGN, actually these are quasars, Sloan selected quasars, and then we constructed their multi-wavelength spectral energy distribution, did modeling of the spectral energy distribution, and then extracted the host galaxy properties. So this is purely observational work. We hope to compare this with simulations. But the key idea of this work is actually look at the star formation and stellar mass relations in these AGN, these quasar host galaxies, and try to see, this is what I'm plotting here in this figure is from Popeso et al. 2022, where there is both simulation and observations of the galaxy, main sequence of star-forming galaxies, okay? So that's the relation between M star and SFR. And our goal was to actually construct the SED, model the SED, and extract an M star SFR relation, a main sequence of these quasar host galaxies, and try to compare with the star-forming main sequence. And what we found, sorry, this might look a little abrupt because I did not have the time to smoothly transit to this thing. And what we found is that for quasar host galaxies, we do see that the main sequence of quasar host galaxies are off from the main sequence of star-forming galaxies at similar redshifts. So now our goal is that if these kinds of predictions are there, then this must be also tested through cosmological volume simulation. So since I'm running out of time, I would stop here, and I would just like to show the pictures of all of the students, apart from the ones I have shown, who have very extensively worked in our group, and these are my grant support. Now, these gentlemen, these 4 men were, I had nice pictures for them. For the other one, Ankit Pal, you can see this guy there is looking at the other side because he has left the field. So he is now no more in astrophysics. So that's a very appropriate picture to show that although he did fantastic work in the X-ray front with Rudrani, he has now looked some other side. And I think I will stop here and then take questions. Thank you very much.
Okay, so thank you so much, Suchetana, for this wonderful talk on cosmological evolution of supermassive black holes, and also on your work on trying to trace Sonia-Zeldovich effect as a probe of black hole feedback across cosmological time as well. So I think we are open for questions. So please raise your hand so that I can see, and then you can unmute. So I don't see any. You can just unmute yourself and ask if that is also fine. If you can't raise your hand, that will be fine as well. Okay. Okay, maybe I can ask a question in the meantime. So
Yes,
I was very, very happy to see that paper that you had on the quasar, the detection from the quasar. That was one of the proofs for
oh,
that
in the
slide.
Leslie et al. Paper?
Yeah, probably that one where they
Yes,
had this detection from a quasar.
this
Yeah,
one.
yeah. So, so I wanted to ask that this was for one particular quasar,
Yeah,
that
that's right.
detection.
So yeah, that's for one particular quasar. It's a very nearby quasar. It's not very high redshift. I forgot the redshift, but it should be around like 0.3-ish. Its name, I think I wrote here, HE05154414. So it's a very targeted observation of one quasar. What you actually like to see is that you want multiple such sources and do targeted SZ observations to see that actually, are you actually getting the the SZ decrement or enhancement depending on what frequency you are observing, and if you are getting, can you have theoretical models to predict it? So yes, yeah, but this is for one. I think there are two more systems I know where this detection has happened in the last 1 year. I think 2023 there was another detection, and recently Mark and his colleagues also wrote another proposal where I'm also a co-I, where we actually got some time to do, based on the predictions that the signal to ratio that we discussed, based on our cosmological simulations, this was used to sort of justify. We got some time in another for observing another quasar. But the other thing is also we want to also do it simultaneously with X-rays, because X-ray and SZ can give you complementary probes, complementary information.
So maybe from an observational point of view, how much time do you need to observe these target sources to be able to detect?
Correct. So I think as we predicted, the deeper the observations, of course, the better. I think we have the integration times. It's of the order of hours, actually. It's not that low. Yeah. To have if I go to this slide here, when you write a paper, you are often very optimistic, and you see 10 sigma detection and all that stuff. So yeah, for these ones, these are like in the hour scale. But yeah, I mean, even in a lower, if you go to a smaller amount of time, then you should still get detection, but that significance might not be as good looking as it was there in the table. So yeah, but yeah, roughly hour scale observations.
Yeah, especially the 42 gigahertz one looks very promising with
Yeah,
the feature.
it is promising in it. I think the other very interesting and promising probe is that we are talking about direct observations that you can do with ALMA, or there is something called NGVLA, the new generation VLA, because you actually need also the sensitivity as well as the angular resolution, because ALMA is interferometry. So I mean, although it's compact array, you don't go to this is all compact array observations. So ALMA has the right kind of resolution to see the bubble, to resolve the bubble, to resolve the system. And also there is NGVLA, which is the new generation VLA, upgraded VLA. So that also we had we are planning to have some predictions for NGVLA, that if we can also, look at these systems through NGVLA.
Okay.
Apart from ALMA, yeah.
Great. All the best for your observations. Okay. So I think since we have no other questions, maybe then we can conclude the talk, and maybe
I
if you
think
have
there
any
is
concluding
a
remarks.
question. Somebody wrote a question, so
Okay.
I may
Okay,
answer
okay.
that. Yeah.
I think it was just a message from Prakriti, but I don't see any other questions.
I think there's a directly message to me. Somebody called Vishal
Okay.
had written
Okay.
that can just little bit more elaborate on the difference between the quasar mode and the radiative mode. That's a very nice question, because all these nomenclature are quite odd. So let me see. Vishal, can you hear me? I hope. So if I now go to this.
Yes, ma'am. Yes, ma'am.
Yeah, if I go to this slide, here I'm not using the word quasar. Here I'm using radiative mode, but you are right. So initially, when I'm talking, like when I was younger, in the 2008, 9, 10, when the first set of cosmological simulations of quasar of AGN feedback were coming, then there were two terms that were used. One is called the radio or the maintenance mode, and the other was the quasar mode, which was actually the radiative mode. But now with more advanced simulations, we know that it's just not radiation that's coming out. It's not the energy that's coming out. Quasars can also have winds, which are mechanical outflow. So now, saying a quasar mode, I do not know what people mean, but in the context of this simulation, the Dave et al. Simulation, the older quasar mode should be equivalent to the X-ray mode. The radiative mode that I'm saying here should not be radiative. I mean, it's actually wind. This is very, very bad nomenclature. So this is actually wind. So in the Dave et al. Simulations, there are three kinds of feedback. One is quasar winds, one is jets, and the other is radiative. But this radiative was, previously, or even now in language, sometimes called quasar mode of feedback, because, jets, yeah, I mean, these are radio loud systems. You see the jets. So people make broadly sometimes this classification that jet and mechanical is the radio feedback and the radiative is the quasar feedback, which happens at high redshift, whereas these ones are mostly lower redshift phenomenon. Did that make sense, Vishal? Am I clear enough? Yeah.
Yes, ma'am. Yes, ma'am. Thank you.
Thank you. Yeah.
Okay, so are there any other questions personally to you, Suchetana, or that was just that one question from Vishal?
It's okay.
Okay, great.
Somebody had a question? Yeah.
I'm asked, if anyone has, I don't personally see any questions on my side. So if someone has still a question, you can unmute and say it. Okay. If not, then maybe we can thank our speaker for today. Thank you so much, Suchetana.
Thank you very much for the talk, and hopefully we will have more interaction with Karina's, because this year, I mean, actually, this year in the ASI meeting, I think we had one of you actually introduce Karina's. So in the gender session, we had discussion, because I am part of the gender group in ASI, and we talked about Karina's. So all the best to all of you. And we'll be having more interaction in the future. Thank you very much.
Definitely. Thank you so much for your time. Thank you.
Thank you. Monami, thank you. I think there are some more comments to me. Thank you.
This is just, Okay.
Okay. So can I leave now? Yeah, with your permission.
Yes.
Yeah.
Sure.
Thank you. And thanks for, many of you are coming like early hours in the morning to attend the talk. So thanks a lot.
It's a pleasure. Definitely.
Bye.
Bye-bye. Manani, are you there? Shall I just, I don't see you. Maybe I can just leave the meeting. I will just leave the meeting.